Okay, so here are a lot of the gas equations we've talked about. Who wants to memorize them all? I don't. You might think you have to memorize all these, and maybe your teacher has even asked you to do that, but you don't have to, because I'm going to show you an incredibly useful trick in this video so that you will never have to worry about memorizing all these guys. Here's how it works. All you have to remember is the ideal gas law. PV equals nRT. And it kind of has a nice ring to it, so it's really easy to stick in your mind. You remember PV equals nRT, and you can use it to get any of these other gas laws whenever you need them to solve a problem. So we can put all these guys away because we don't need any of them anymore. And I'll show you how to use PV equals nRT for this trick. So let's say that you're given a problem like this, okay? We have a before and after, we have pressure and temperature are both changing. So we look at the variables we're dealing with, as I just said, pressure and temperature. And what I want to do is I want to take PV equals nRT, the ideal gas law, and rearrange it so that the variables I'm interested in, pressure and temperature, are by themselves on one side of the equation. Doesn't matter which side it is. Okay, so pressure and temperature. So to get P and T by themselves, I'll first divide both sides by V here. And then V over V will cancel out. So now I have P equals nRT divided by V. And I want to get T on the other side of the equation so it can join P. So I'll divide both sides by T. And now T over T cancels out. And I'm left with PT, P over T, equals nR over V. Okay, so we have P over T on one side of the equation. Now, it turns out that if something is on one side of the ideal gas equation, you can double it on the other side, doing a before and after thing. Here's what I mean. We can take this P over T and turn that into P1 over T1. There's a before. And then we double it on the other side, equals P2 over T2. What we've actually just done is we've created Gay-Lussac's law. But I didn't have to memorize it, and all I had to do is take PV equals nRT and figure it out from there. Okay, let's look at another example. Here is one where I have an initial pressure, a final pressure, initial volume, and final volume. So the variables that I'm interested in are pressure and volume. As before, I want to rearrange the equation so that I have pressure and volume by themselves on one side. That was easy. The ideal gas law is already written so pressure and volume are by themselves on one side. Okay? So what we do now is we double this PV on both sides of the equation, doing before and after. So P1 times V1 equals, double it on the other side, P2 times V2. And now I can plug in my variables and solve for V1. And check it out. What I did was I used PV equals nRT to come up with Boyle's law. Okay, you're probably getting the hang of it. I'm going to do two more examples, but if this already makes sense, go ahead and move on. Now, one question that I do often get is, how do you know which variables you want to rearrange the equation for? You know, teachers and textbooks don't always ask questions where they just say V1 is this, N1 is this, and so forth. So if you're given a word problem, it can be a little bit trickier to find out what variables you're using and whether they're, V1, N2, or whatever. So if you're having a little trouble figuring out what the variables are, watch my video called Which Gas Equation Do I Use? And that will tell you how to read a word problem and figure out which of the variables you're working with, okay? So this one, we're going to be using volume and moles. So we want to rearrange the ideal gas law so that I have volume and moles by themselves on one side, okay? I will get rid of P so that I have only V alone on this side. Divide both sides by P. And then I have V equals nRT divided by P. And I want to get n to the other side. So I'll divide both sides by n here. Cross that out. And then I have V over n equals RT over P. I have this guy by itself, so let me double it before and after on both sides of the equal sign. V1 over N1 equals V2 over N2. And what I did there was I came up with Avogadro's law. One more. This is for one that's a little bit trickier. I have a before and after here where three variables are changing. I have volume, pressure, and temperature. So everything that I've been doing up until this point has just had two variables changing, but it's no big deal. You can use this technique for any number of variables. So volume, pressure, and temperature I want to get on one side of the ideal gas equation. So I already have pressure and volume here. So how about I divide both sides by T to get them all together here. Cancel this out. And I'm rewriting it, but it really doesn't matter what's on the right side here. All that matters is what's on the left side here when we get these together. So I now turn this to P1 times V1 over T1, double it on the other side, equals P2 times V2 over T2. And that was the, where is it here? That was the combined gas law. But hey, I didn't have to memorize it. So that is how you can use this technique to come up with any of the gas equations you need and not have to worry about memorizing. But you will have to be able to read a word problem and figure out which of the variables you're working with. So again, if you're having trouble with that, watch that video that I talked about earlier and you should be all set. So how do you choose the right gas law when you're trying to solve a problem? That's going to be the focus of this video. Maybe you're all set when somebody says, okay, use Boyle's law for this question and Charles' law for this question. But then you get thrown off a little bit when you're just given a question and you have to figure out which one of these gas laws you use to solve it. We'll look at that here. This video may also be useful for you if you have trouble figuring out the variables in an equation. In other words, if you have a hard time reading a question, figuring out what should be V1 and what should be P2. We'll look at how both of these things come together, and we'll use that to help us solve these equations. So, first question here. A sample of gas takes up 45 liters. After being compressed down to a volume of 12 liters, the sample has a pressure of 5.7 atm. What was the original pressure? So when you're doing these gas problems, the first thing you want to think about when reading a question is there a change going on? Is there a before and after? So, is there a before and after with this question? Yes. A sample of gas takes up 45 liters, and then it's compressed down to a volume of 12 liters. So I'm going to write these variables out so that we can keep track of them. And that may be a useful thing for you to do at first before you get the hang of it. Okay, so there's a before and an after. The before, we have a volume, V1, the initial volume, of 45 liters. Then we have this after volume. The volume gets compressed down to 12 liters. So that's before and after volume. What about other variables? So we have this pressure of 5.7 atm. What's that? This is after being compressed. The sample has a pressure of 5.7 atm. So that means that the pressure, P2 here, is 5.7 atm because it's after this change occurred. And the question asks, what was the original pressure? So what was the pressure before this change? This, P1, is what we're going to be solving for. So we set up and figure out the variables like this. Now we need to figure out which of these gas laws we're going to be using. We want to find the gas law that has V1 and P1 and V2 and P2 in it. And that is going to be Boyle's law, because the variables that we're solving for match the variables in the equation. Let's look at another one. A balloon takes up 32 liters of volume at 20 degrees Celsius and a pressure of 212 kilopascals. At what temperature will the balloon have a volume of 50 liters and a pressure of 300 kilopascals? So just like before, we want to ask about a change. Is there a change? Is there a before and an after in here? Or are there maybe just two different situations? Well, there are. Because we start out with this volume and temperature and pressure, and then it asks at what temperature will this other stuff happen? Okay? So that would be a change to another set of circumstances. So the original temperature, temperature 1, is going to be 20 degrees Celsius. And temperature 2, at what temperature would this other stuff happen? That's what we're solving for, okay? Let's look at the other variables. Let's start with volume. Okay, volume. The balloon initially takes up 32 liters. So that's V1. Does the volume change? At what temperature would that volume, would that balloon have a volume of 50 liters? So that's what it would be after this change. We'd have 50 liters. And how about pressure? Our initial pressure, before we change the temperature, is 212 kPa. And then we change the temperature to T2, and we're looking for a pressure of 300 kilopascals. So here are our variables. Which of these equations have the variables we're looking for? We want T1, V1, P1, and T2, V2, and P2. So we're going to be using the combined gas law because these guys all fit, and we'll rearrange it to solve for T2. All right. Those two examples that we looked at were relatively straightforward. Now I'm going to do a few that are a little bit trickier because they have, some of them have some extra information in there that can sometimes throw people off. So here we go. As I'm reading it, I want you to be thinking, is there a change? Is there a before and after? And then we'll see how we set up the variables, okay? At a temperature of 65 degrees Celsius and a pressure of 1120 millimeters of mercury, a large balloon takes up 25 liters. What will the volume become if the pressure is lowered to 5 degrees Celsius? Okay, is there a change? Absolutely, because temperature of 65 degrees, which is then lowered to 5 degrees Celsius. So that's change. We have a before and an after temperature. So before, after. The before temperature is 65 degrees Celsius. The after temperature, we lower it to 5 degrees Celsius. 5 degrees Celsius. Let's look at what's happening with the other variables now. Okay. We have a pressure of 1,120 millimeters of mercury. So we can call that P1, millimeters of mercury. What happens to the pressure? The pressure doesn't change. There's no P2. We'll come back to that in a minute. Let's look at volume here. At the initial temperature, we have a volume of 25 liters, okay? V1 is 25 liters, and that says what will the volume become if the temperature is lowered? So it's this after volume that we're going to be solving for. So the variables that we're given in the problem are T1, T2, V1, V2, and a P1, a pressure. But here's the thing. P1 doesn't change. It's given to us at the beginning, but there's not a P2, there's not an after, so we assume that P1 stays the same. It's what we call a constant, something that doesn't change throughout the course of the equation. Because P1 doesn't change, we don't want P1 to be in the equation that we use. So don't be confused and use the combined gas law because it has these guys in it. Instead, we don't worry about P1 because it doesn't change, and we want only an equation that has T1, V1, T2, and V2 in it. So we're going to be using Charles' law. We solve only for these things that change, that have a before and after, and we leave out these guys like P1 that are constants, that do not change over the course of the problem. So if one of these questions gives you some extra information, don't get thrown off. Just ask yourself whether or not it changes over the course of the problem. If not, leave it out. Okay, at a temperature of 45 degrees Celsius and a pressure of 250 kilopascals, how many moles will fill a container that is 16 liters in volume? Okay, as before, is there a change here? Is there a before and an after? No, there's not. There's not a change. Here are the variables. We have a temperature of 45 degrees Celsius. You have a pressure of 250 kilopascals. The question is how many moles will fit in a container that fits this description. So moles is going to be what we're solving for. And then this is a container that has a volume of 16 liters. These are the variables, but there's no before and after. So to solve for moles here, we want to use the only equation here which doesn't have a before and after, doesn't have a 1 and a 2. And that's all the way down here, the ideal gas law. It's got P, V, N, and T, and we know what R is. It's a gas constant. But there is not a change that takes place in this equation. So the ideal gas law is the equation that you want to use whenever you're solving a gas problem like this. It gives you these variables, but does not have a before and after or two different settings in it. Okay, one more. This one's a long one, and you may guess that it has some extra information. We'll figure out what we need and what we don't. Again, think about a change. Is there a change taking place, and what is it? A sample of gas in a rigid 20-liter container has a pressure of 2,200 millimeters of mercury, and it's placed outside in the morning when the temperature is cold. Throughout the day, it warms up, and by the afternoon, the pressure reaches 39 degrees Celsius. Okay, right there is our change. Cold to warm. So there's a change in the pressure. A change in the temperature, okay? Anyway, reaches 39 degrees Celsius, and the pressure inside the container is 2,700 millimeters of mercury. What was the temperature in the morning? So we have a before and after. The after temperature we know right away, T2. It's 39 degrees because we said it was cold in the morning, it warmed up. The question is asking what was the temperature in the morning? So what was the temperature before it warmed up? That's going to be T1. And we don't know what that is. That's what we're going to be solving for. Let's look at these other numbers here. We say a sample of gas is in a rigid 20-liter container. So we could say something like V1 is 20 liters. Does V1 change throughout the course of this equation? Throughout the course of this question? Could read this? No. There is no other mention of volume changing. So we're going to assume that volume is a constant throughout and not something we need to worry about when we're picking an equation. Okay? Let's look at the other numbers here. We have a pressure, this is in the morning, of 2,200 millimeters of mercury. So I'm going to call that pressure 1. 2,200 millimeters of mercury. Okay? Does that change? Is there an after pressure? And yes, there is. Throughout the day, it warms up, and by the afternoon, the pressure inside the container is 2,700 millimeters of mercury. So that's P2. Here are the variables that we have. T1, P1, T2, and P2, and I don't worry about V1 because it stays constant throughout here. So the equation that I want will have temperature and pressure before and after. So I will use Gay-Lussac's law, which has P1, T1, P2, and T2. So when you're solving these problems, it can help at first to figure out what your before variables are and what your after variables are. Figure out what changes and what doesn't. If it doesn't change throughout the course of the equation, leave it out. And then look for the gas law here that has the variables that change that you're solving for from the beginning to the end of the equation. If things don't change, chances are you're going to be using the ideal gas law. So that's how to know which gas equation to choose when you're given a problem.